We're continuing on chapter 9. We've been talking about solutions. We talked about some concentration, I think, last time. We talked about percent mass to mass, which is the mass of the solute over the mass of the solution times 100%. Remember, again, when you use this one, the bottom is the important one. You need to make sure that you do get the mass of the entire solution, not just the solvent, as it is commonly sort of separated out in those problems. Percent volume to volume, like in alcohol, that is the volume of the solute divided by the volume of the solution times 100%. This is, again, kind of like milliliters over milliliters. And we also talked about, I think, percent mass to volume. And that's the mass of the solute over the volume of solution times 100%. Remember that if you are sort of given a percent concentration, you could turn it into a usable conversion factor. So if we had a 3.25% by mass calcium chloride solution, that means that basically we have 3.25 grams of calcium chloride in 100 grams of solution. Or you could flip it around, use 100 grams of solution is 3.25 grams of calcium chloride. We also talked about equivalents, I think, as well. And equivalents are really based on the charge. So if you had something like calcium, the charge is 2 really here. And you could use it as a conversion factor of 1 mole of calcium ions would have 2 equivalents. And very common, sometimes solutions are given in equivalents per liter or milliequivalents per liter, as we talked about there. Any questions on that stuff there? All right, so continuing on, we talked about these other concentration units, but really the major sort of concentration unit that's used for solutions is molarity. And molarity is abbreviated with a big M. And molarity is the moles of a solute over liters of solution. So molarity is moles per liter. You should think of this sort of like a formula, because oftentimes we'll use molarity, volume, and moles to calculate any of those three. So if you wanted the liters, it would be the moles divided by the molarity. If you wanted moles, which is a common sort of calculation, you take liters times the molarity. So molarity is moles per liter, but oftentimes in chemistry, we do sort of rearrange it and use it as sort of like a formula to solve for liters or moles. You should really always convert the volume into liters so everything cancels out correctly. If you have a solution that is 4.75 molar sodium chloride, it's important, I would highly recommend not leaving the big M as you're doing the calculation. And that's because most of the time people really have no clue as to like kind of where the liters part of that number is. So if you did have something like this, you could convert it into really like a conversion factor. And you could say that there are 4.75 moles of sodium chloride per liter. So molarity is always moles per 1 liter. And that is the way you can use it in a calculation. You could also use it like a conversion factor if you needed to flip it around and have liters up on top and doing a little dimensional analysis. You could put the moles on the bottom. But definitely get rid of the big M as you're using it in the calculations. Again, I've seen a lot of people, again, not really understand what the big M really stands for, and that there actually are 2 units sort of there. And like I said, a lot of times people really can't even understand where the volume part of it comes into play. The higher the molarity value, the stronger the solution is, because it has more solute dissolved in it. So if we have a 1 molar solution of something like sodium chloride, that means that we have 1 mole of sodium chloride in enough water to make 1 liter of solution. how concentration and ions work together is, for example, if we have something like sodium chloride in solution, as we talked about, it will break apart into a sodium ion and a chloride ion, which means that if the molarity of the entire thing here is 1 molar, you could kind of do like stoichiometry with it to figure out the concentration of just the ion by itself. So if I was interested in that solution, what the concentration of the sodium ions were floating around, it's basically a 1-to-1 relationship between the whole thing and the sodium ions. And that basically means that the concentration of the sodium ion would also be 1 molar in this case. It is also a 1-to-1 relationship between the sodium chloride and the chloride. That means if you were interested in just the chloride's concentration, it would also be 1 molar. So sometimes you're interested or asked about maybe not the whole ionic compound in a solution, but maybe concentration of the ions are. Now, it does change depending if we had, say, the same sort of 1 molar calcium chloride solution. And the difference here is when calcium chloride breaks apart, you get a calcium ion and you get 2 chloride ions. And what that means, if we were looking at the concentration of each of the ions, if this guy is 1 molar, the calcium ion is still a 1-to-1 relationship, which means we take 1 times 1 is 1 molar. When we look at the chloride ions, it's for every one of the whole units, you get actually 2 of the chloride ions. So what it actually does is you need to actually take the concentration and multiply it by 2. And the concentration of the chloride ions in that solution, sort of the quick way that you could calculate the concentration of ions in solution, basically figure out how it breaks apart. If it breaks apart into a kind of a 1-to-1, the concentration of the whole thing and the ion would be the same. Like in this example, if it breaks apart into a 1-to-2 relationship, you do have to multiply the concentration by 2. The reason you have to do that is the short calculation part. Here's the actual way that we actually get there. If you started with 1 molar calcium chloride, that would be 1 mole of calcium chloride per liter. Again, it is a 1-to-2 relationship, just like in stoichiometry, 1 mole to 2 moles. And if you did that part of the calculation here, 1 mole of calcium chloride is 2 moles of chloride. The moles of calcium chloride would cancel. That is basically why we're multiplying this by 2. And we would end up with 2 moles of chloride ions per liter. So that's the long version of just multiply it by 2, basically, and you'll get the same thing. So it really is like the multiple relationship in terms of how the ions break apart in solution. Question on that there. And obviously, if we did it for the calcium, the only difference is the mole to mole relationship in the middle would be a 1-to-1 relationship. So we would have 1 mole of calcium chloride gives us 1 mole of calcium ions. The moles of those guys cancel and we end up with 1 mole of calcium per liter. So again, that is the long version of just multiply it by 1, what we did right in that case. Question on that there. What's that? Yeah, so really the quick way to figure out, again, and this is specifically if you were not interested in the whole sort of compound, but just one of the ions that are floating around, whatever the coefficient is in front of that ion is basically what you would multiply the molarity of the whole thing by. So if it was a 1-to-1, you times it by 1, 1-to-2 times it by the proper concentration for that particular. Other questions? Okay, so let's take a look at an example here, and obviously we want to calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Potassium is 3910 on the periodic table. And BR is 7990, I think. All right, so take a moment here. We want the molarity of the whole thing, KBR in this case. Okay, let's look at this. So we're looking for the molarity. So once again, molarity is moles per liter. And we obviously have the liters part of it right here. We do not have the moles part, but we do have grams. So to get to the moles, we have to do a normal sort of grams to mole conversion, which would use the molar mass from the periodic table. So basically, in this case, we're just going to add those two together, and that's going to give us 119 grams per mole. So to convert our grams into moles so that we can calculate the molarity here of the KBR using the molar mass from the periodic table of 119 grams per mole. Grams will cancel, and here gets us 0.131 moles, and that is the top part of what we need. Now we have everything we need to calculate the molarity. We'll take our moles, we'll divide it by the liters here. And if we do that, 1.25. Looks like 0.105. Now you can leave it one of two ways. The units here do not cancel out, so the number always stays with the moles and it's always per 1 liter. Or if you want at this point, once you get the answer, you can just write big M and you could write whatever this is here, KBR. So you could do it either way in this case. Question on that there. So a very common conversion that you oftentimes will have to do when you're calculating the molarity of something is to go from grams to moles using the molar mass like we've done before. Another very common conversion that you have to do is to convert the volume to liters. So again, that 1,000 milliliters is a liter. That also is a very common sort of conversion that's usually used here with molarity. Any questions on that there? All right, so there's some of our concentration units. All right, let's try another one here. What is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar solution of sodium nitrate? Sodium is 2299 on the periodic table. Nitrogen is 1401, and oxygen is still 16. Okay, let's take a look. So once again, we're obviously dealing with molarity here, which is moles per liter. We are looking for the grams. We are given the volume, so we have that guy. We are also given the molarity, which means we have that guy. So again, it would make sense to solve for moles because once we have the moles, we again can use the molar mass to go from moles to grams like we've done before. In this case here, I am going to convert the molarity into a more usable conversion factor, which is moles per liter of sodium nitrate. And again, you can use it like that, or you could flip it around and put the moles on the bottom and really just work it like a dimensional analysis problem. So we have 2.5 liters. And that is in the correct unit. Once again, if the volume was in milliliters, you would need to do a conversion to convert it to liters. Here, we're going to use the conversion really on the left here so that the liters cancel. The liters here will cancel, and we will end up with 2.5 times 0.150. This gives us 0.375 moles of our sodium nitrate. At this point, it's just a conversion now between moles to grams. So we'll come up here to our periodic table, and we have 1 sodium at 2299. We got 1 nitrogen at 1401, and we got 3 oxygens at 16 here. And that gives us a molar mass for that guy of 85, it looks like. Yeah. So we're going to use the molar mass from the periodic table to do the last step here to find how many grams we would need. And we're going to want grams up on top. So we'll put the 85 grams up top and a mole on the bottom so that they do cancel. And looks like here we end up with about 31.9 grams of sodium nitrate is needed in this case. So if you wanted to make a solution that had a concentration of 0.15 molar in this case of sodium nitrate, you would scoop out about 31.9 grams of it, add some water to dissolve it, and add enough water to end up with a total volume of 0.5 liters. Give it a mix and mix, shaky, shaky, and you will have a solution that is 0.15 molar. Question on that part there. Okay, so let's take a look at a few more here. So this is what we were talking about earlier in this case. And the concentrations of ions in each of these individual solutions. So looking at this one here, if we started with sodium sulfate, and it had a concentration of 1.2 molar. Again, if we're interested in the ions, we want to make sure that we kind of break it apart correctly. There's going to be 2 sodium ions. And there will be 1 sulfate ion that it will break apart into. So once again, as we were talking about, we can use really like a stoichiometry sort of relationship. For every one of the whole things, we do get 2 of the sodium ions floating around. So we take 2 times the concentration of the whole thing, and that will get us 2.4 molar, would be the concentration of the sodium ions. When we look at the sulfate, it is a 1-to-1 relationship, which means we basically take 1 times the concentration of the whole thing, which would give us 1.20 molar, which would be the concentration for sulfate in that particular solution. The concentrations are not additive. Obviously, they don't add up to 1.2. It's really proportion wise. Basically, if you just logically think about it, when you drop this guy into the solution, you basically get twice as much sodium ions floating around as you do sulfate ions. So it's twice the concentration of sodium in that particular case as it is sulfate. Question on that one there. We look at this one here, we have a solution of potassium chromate, which is what that is. And the entire concentration there was 0.75 molar. When potassium chromate breaks apart, you do get 2 potassium ions and you get 1 chromate ion. Once again, we'll just do a simple sort of stoichiometry. It's a 1-to-2 relationship. So if we wanted the concentration of just the potassium ions that are floating around in there, we're going to take 2 times 0.75. And that would get us there 1.50 molar. And when we look at the whole thing to our chromate, it is a 1-to-1 relationship, which means we simply take 1 times the original concentration. Gets us 0.75 molar in this case. A question on molarity or how to relate molarity to individual ions. You don't have to do individual ions. In a lot of cases, you look at the whole thing, but sometimes you are asked about kind of just the individual sort of ions that are floating around. Any questions on that there? Now, just to illustrate something that we talked about a little bit earlier, which was equivalence, right? And when we look at these guys' concentrations here, let's do this top one here. If I wanted to know, instead of what is the molarity of each of these ions, but I want to know what is the equivalence per liter of each of these ions, both the sulfate and the sodium ion. We could do what we talked about last time, which is, in this case, we would look at the sodium ion. And from that, it has a 1 charge, which means for every 1 mole of sodium ion, you get 1 equivalent. That means if we took the molarity of just the sodium ion here, that would be 2.4 moles of sodium per liter. Using our equivalence as a conversion factor, 1 mole of sodium gives me 1 equivalent. And that would give me basically 2.4 equivalents per liter of sodium ion that's in that solution, as the moles would cancel. When I look at sulfate here, for every 1 mole of sulfate, how many equivalents will I have? 2 equivalents, right? Because of the charge. And if I take the concentration of sulfate in that particular solution, that would be 1.2 moles of sulfate per liter. Using my equivalent conversion, 2 equivalents per 1 mole of sulfate. The moles of sulfate cancel, and I end up with 2.4 equivalents per liter of sulfate. In terms of equivalents per liter, are they different or the same? They are the same in a solution, and that's because when we make an ionic compound, right, we balance out the charge to 0. And that means when you calculate the concentration and equivalents per liter, or even if you converted that to milliequivalents per liter for a ionic solution, both the cation and anion should end up being the same, because these are both based off the charge, and the idea of an ionic compound, right, is you balance it out to 0. So they should basically cancel each other out in terms of the positive charge that's sort of floating around that solution and the negative charge. Any questions on that there? Free add-on for free today. There we go. All right. The next thing we're going to talk about is actually dilution. And dilution is a process where we basically add more solvent to a solution. The result of adding more solvent to a solution is your concentration actually goes down. So why would your concentration go down? If we think about the definition of molarity, that is the moles of the solute divided by liters of solution. When we add more solvent, like water, the only place in this equation where solvent is found is right there. So when we add more solvent, we're actually increasing the volume of the solution, which means we have a larger number on the bottom, smaller number on top. The molarity goes down. The actual moles stay the same, but the molarity will decrease because of that, because this bottom number here is getting larger when we add more water to it. So the molarity comes down. So the moles of the solute before the dilution will equal the moles after the dilution. In most cases, it is just water a lot of times you're adding, but remember that water is not necessarily always the solvent that's used, but basically we're adding more solvent to that, which will lower the concentration. Here's one fancy way you could do it. You could use what's known as a volumetric flask, which is expensive because it has one line, basically. And basically you'd add a little bit of water, add your more concentrated solution to it, and then top it off with a little bit more water. And now basically we added more solvent, the molarity of that solution will come down in here, and you would mix it up. So to calculate the concentration needed in a dilution, because molarity really is the most common unit that's used for concentration, most people will use this dilution equation as M1V1 equals M2V2. And that is molarity and volume of your more concentrated solution. And that is the molarity and volume of your more dilute solution in most cases. It really doesn't matter, but that's usually how it is sort of arranged. Now, Some people will use C1 V1 equals C2 V2, and C is just generic for concentration. And what I mean by that is you really could put into this formula any of those units of concentration we talked about, like percent mass mass, percent volume volume. You know, you could do any of those sort of concentration units. But once again, molarity is really the most common sort of unit that is used. Now, a couple of things that you should be aware of when you use this dilution equation. That is the one equation where you do not need to necessarily convert your volume to liters. You can leave it in milliliters and everything will work out okay. Because if you take molarity here times milliliters and then divide by milliliters on the other side, those milliliters will cancel and you'll be back to molarity. Now, if you are using molarity by itself, not using this equation, just molarity problem, not a dilution problem, you need to convert it to liters. Otherwise, you most likely will get the wrong answer. So make sure you convert it to liters. If you want to convert it to liters when you use the dilution equation, you can, it's fine. But if you want to leave it in milliliters when you use this equation, everything will work out okay if you want to do it that way. Because by the way, technically, as was on the other side, if you take milliliters times molarity, you actually don't get moles, you get what is known as millimoles, which then if you divide it by milliliters, the millis cancel and you get moles per liter, which takes you back to molarity. So technically, if you times it by milliliters, you get millimoles, not moles. So again, if you're using molarity by itself, convert the liters, the volume to liters. If you're using this equation, you can still convert to liters or leave it in milliliters, so it'll be okay. All right, so let's try one here. What volume of 19 molar sodium hydroxide is needed to make 1 liter of 0.15 molar sodium hydroxide? Okay, so let's take a look. So what we got going on here is we have a more concentrated solution of sodium hydroxide. We want to make a less concentrated solution of sodium hydroxide here. So basically, we got a bottle of 19 molar kind of sitting over here. And we want to make a new sort of solution that has a total volume of 1 liter, right, or 1,000 milliliters, and has a molarity of 0.15 molar. So we could use our dilution equation to help us figure that out. M1 V1 equals M2 V2. It doesn't really matter which one, honestly, you label ones or twos, as long as you keep the appropriate numbers together. Obviously, these two go together and this one doesn't. Typically, again, the more concentrated guy is the one. So that's going to be basically 19 molar. We do not have V1. We have 0.15 molar here, and we have 1 liter. So we're basically going to divide this to the other side. That would give us V1 is 0.15 molar times 1 liter divided by 19 molar. The molarities will cancel, and that will leave us in liters. 0.15 divided by 19 looks like. And that will get us something like 0.0079 liters, or that if you multiply it by 1,000, gets you about 7.9 milliliters, basically. That is 7.9 milliliters of the sodium hydroxide solution that you need. What that basically means is I'm going to reach into my more concentrated bottle here. I'm going to take out 7.9 milliliters. Now, in this case, would I put in there 1,000 milliliters of water to get me to 1 liter? I would not, because if I put 1,000 milliliters of water, my total volume at that point would be like 1,007.9 milliliters, which is too much, and my molarity would not be 0.15. So a very common question, sometimes asked with dilution problems, is how much like water would you put in there? So a lot of times, if you need to figure out how much water you would put in there, or solvent, you take a lot of times V2 minus V1. V2 is usually your final volume of your diluted solution. V1 is the more concentrated volume. So in this particular case, if we wanted to do that, we would end up with 1,000 milliliters, which is 1 liter, minus the 7.9 milliliters that we put in there. that means that we basically would need to put in there about 992.1 milliliters of water. So we would top this guy off with 992.1 milliliters of water. At that point, we'll give it a nice mixy, shaky type of deal. We would then end up with 1,000 milliliters of the volume, and we would end up with a solution that has a concentration of 0.15. So remember, that's a very common sort of question about dilution. Is oftentimes will ask, how much water you need to put in there to make the solution. Question on that there. The answer to this question is obviously 0.0079 liters or 7.9 milliliters, obviously, is what this question was asking. All right, let's take a look at another one here. What volume of water is needed to make 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? Once again here, we have a more concentrated solution. We want to make a more dilute solution. So in this case, we got basically a 5 molar bottle here of calcium nitrate sitting there. And once again, we want to make a kind of new solution that has a total volume, in this case, of 500 milliliters and should end up with a molarity, bless you, of 0.25 molar in this case. So once again, this is a situation where we could use our M1 V1 equals M2 V2. We have the more concentrated concentration, we have the more dilute and the final volume. So once again here, we don't have V1. We're going to send M1 to the other side, gives us V1 is equal to M2 V2 divided by M1. Once again, in this case, if you want to convert the volume into liters, you can, but you don't really need to using this formula. We'll take our molarity of M2, which is the more dilute 0.25 molar. Again, I'm going to leave it here in milliliters because it will work out okay using this formula, divided by the volume, the molarity of our more concentrated solution. And once again, this works out okay because molarity here and molarity here will cancel, and that will leave you milliliters. And if you do that, you will end up with 25 milliliters here. That is 25 milliliters of calcium nitrate. That means I would go to my bottle, take out 25 milliliters of it. Is that the answer, by the way, in this question? It is not. We're actually looking for the water in this case. So it wants to know how much water is there. So our final volume is 500 milliliters. We just put in there 25 milliliters of the actual solution, which means to get the rest there, we need about 475 milliliters of water to be added to this. And then we will have our total volume that we need, which is 500 milliliters. Again, you would mix it up and you would have a solution that has a concentration of 0.25 molar. Question on dilution. I would say most people always seem to miss that question, part of the question there of how much water to add. Yeah. All right, we will lay it up there, I think, for today.